Next up, we have Daniel and Simon from the Big Dutchman, and they're going to be talking about the sort of technology and infrastructure that you can use, such as air scrubbers and the Zoletto systems, which improve welfare and emissions. So over to them.
My name is Simon League. I am the Business Development Manager for EnoPlus. We are part of the Big Dutchman group of companies. And I have been asked to speak to you today about the role of air scrubbers in reducing ammonia. I would like to thank the AHDB for inviting us to do this. Yes, so thank you. So what am I going to talk about this today? Well, I'm going to cover air scrubbing and how modern day air scrubbing meets the needs of planning and mitigation of ammonia in accordance with the best available techniques. I'm also going to explain how air scrubbing works. And I'm going to also cover a little bit about how can we achieve return on investment through using the energy gathered in an air scrubber to precondition houses to lower energy consumption, usage and costs, and improve production. And at the end, I'll give a little bit of evidence through an example of how that works. So, first of all, the BAT. Well, the section that we're really referring to in the BAT is a 40-page document which in short covers the types of air cleaning systems available today, the environmental benefits that can be achieved through air scrubbing, performance and operational data about those environmental benefit, a little bit about ammonia efficiency as a proportion of air treated. This is quite an important point when designing air scrubbing. Odor, types of air scrubber from water, chemical, biological, and multi-stage. What the expected resource consumption in terms of water and electricity is. Partial air scrubbing. Again, this is something that's in fairly common practice. And then there's a little bit on dry, dust filters and water traps, which I won't cover today. And finally, we talk about the investment, what it costs. So saying that, where are we really? Well, single or multi-stage air scrubbers are basically designed to achieve levels of abatement in emissions, and that is namely ammonia, odor, and dust. And on the screen, you can see some examples, the ranges that are published where the BAT suggests we should be heading in terms of abatement. These rules and regulations that are set down, or protocol as it were, are very much based on proven and tested methods. And on the right, I've kind of listed 3 organizations, the DLG in Germany, BWL in the Netherlands, and the more internationally recognized VERA organization, where air abatement systems can be tested and proven against the protocols that are laid down. Okay. In principle, what is normally suggested is that we are cleaning air from a centralized point of extraction. Obviously, that is the most convenient thing to do. In other words, if we're pointing the air in a certain place, we can then target the air abatement there. When we look at existing buildings, obviously, some of the challenges we may face where, for example, the extraction is along the top of the roof, retrofitting these systems can be a challenge. But saying that, it is possible, and we do that on a regular basis. The other important point to perhaps draw out of the BAT is the fact that, and the protocols are very much based on calculations based on the maximum air capacities from a system. It is quite an involved topic of discussion, but basically, depending on what is determined as the maximum air capacity or what is required by the authorities, calculations on the capacity of an air scrubber for a particular production is based on that. maximum air requirement, namely in the hot periods during the summer. I'm going to, as I move on, talk a little bit about different types of air scrubbers. I'm not going to cover them all today because we haven't got the time, but in principle, available in the market today, we have chemical air scrubbers, which is air scrubbers that are mainly focused on the reduction of ammonia, and also biological scrubbers where we are more focused on the reduction of odor. We do see in the market combination systems, sometimes 2-stage or a 3-stage air scrubber. A 3-stage air scrubber will do a level of dust removal through a washing process with water. It'll then carry out a chemical process to reduce ammonia, and finally a biological process to reduce the odor. These systems, of course, are more expensive than a single stage, and so only usually recommended where the law dictates a high level of reduction. But of course, saying that, the modern day single stage scrubber does achieve quite a high level in itself. We have two approaches, the push system or the pull system. Again, this will depend on what the regulations insist on. The normal rule is go for a push system because it's simpler, it's cheaper. A pull system is usually put in place where, for example, the ruling says we have to extract air at a certain speed, at a certain height from the building. And then moving on, we have two types of scrubber that's in common place today. And here are a couple of pictures. Here are a couple of pig buildings based in the Netherlands. We have the module, which is a self-contained box made from plastic or palletin. And this houses not only the scrubbing table, the mechanism for washing, but also the technical room, usually in a cabinet at the side of the box. The advantage of this system, of course, being self-contained, not only can it be tested during its build process before shipping, but also once it reaches site, it is a relatively simple system to install. It doesn't require any additional building work. The image on the right is of a pig house where we have two built-in scrubbers. I don't know if you can follow my mouse, but at this side of the building, there's an air scrubber when it has an exhaust corridor going down the middle of it. And these systems basically use the same technology, the same design, but there's a certain flexibility in terms of the capacity that you can deal with. This building on the right is a finisher house of 20,000 finishers. Clearly that's producing a high volume of air, which would be difficult to clean with a modular box that has a limited capacity, especially when you consider we have to transport these systems around the world. So both systems achieve the same thing. The one on the right tends to be used in the context of larger production. The trend is today towards more simple, self-regulating, easier to maintain air scrubbers. So if we drill down a little bit into the system, going around, I've numbered the images to easy to follow. Here we have an image of a module sitting at the end of the house, which is attached to a pressure room. And in this particular system, the exhaust is running through the top of the house, is running into this pressure area, and then it goes down into the scrubber and out through the top. So when we move to image number 2, this is a shot from inside the pressure room. I think you can perhaps see on the top left the images of the fans. So the air is coming down there, going down into the box, going underneath, and then on the right of there, we see the shower section where the water will come through the packing material. So the air comes up through this legged area into the packing material, and then below that, through the packing material into the sprinkler section. And what we have here is a series of piping that is housing sprinklers, and the sprinklers spray the treated water across the packing material. That drops down into the shower section. The contact with the polluted air and the wash water happens during the packing material stage of the scrubbing process. Then the air comes up through the sprinkler, out through the top, through what we call the drop catcher, which is just basically an exhaust filter that allows us to contain any moisture or droplets that may escape into the atmosphere. And then on the bottom left, we've got an image of the technical room, which is where the mechanism for controlling the pumping of the wash water around the system is housed. Moving on, this is again drilling down into the guts of the scrubber. I think it makes it clearer here. This is the table area. The arrows show the direction of the air coming in underneath the table. They will then be forced up because the table is in a closed area, forced up through the packing material and out through the top. So where we have the drop catcher, sprinklers in the middle, and then the washing table and supports underneath it. So a breakdown. Going across, we have an image of the technical area. This is what we could refer to as a skid. It's an engineering frame. In commonplace today, these systems are fairly standard. So in here we have the pipe that pulls the water out through the scrubber pit. There's a filter that is obviously retaining any dirt that gets into the washing water to protect the pump, and then the water goes along the pump. The modern systems today are fairly self-regulating, so they'll have a series of sensors. Conductivity, which is measuring it's basically the electrical charge within the salts, the positive and negatives, and also measuring the levels of pH, the acidity or the alkalinity of the wash water. And on top of that, we also would include a pressure sensor. It's very important to be able to maintain how clean the scrubber is, so that the pressure sensor is checking the back pressure in the air. If it gets high, then it's usually an indicator that the packing material is getting blocked and it needs to be washed out. But on the whole, these systems are fairly self-regulating, because what happens is, as the system detects that the conductivity is getting high, in other words, the level of nitrogen in the wash water is getting high, or the pH is going out of its optimal zone, then what happens is the system feeds off a level of the water into a waste tank and then replenishes the water with fresh and fresh acid, if it's in the case of an acid scrubber. So it's very self-regulating. On the whole, needs very little maintenance. An important point, and an innovation today is obviously the use of data. It's very important that we can manage these systems and have a good understanding that they're performing well. And as such, most modern systems today will have the ability to connect either to a computer on site, or preferably to the cloud, where data is stored and reports can be made to be shared to analyze yourself as a farmer, or perhaps even to be shared to the authorities to say that your air abatement system is working in accordance to the regulations laid down in your permit. This slide shows a little bit talking about what's the protocols that are laid down in the BAT. I mean, obviously, air scrubbing is a fairly flexible technology, so it's almost a case of it can deliver what we throw at the problem. I mean, today we also have air cleaning systems that reduce ammonia from composting, where we're talking very high levels of ammonia ppm. 3,000 ppm is pretty common, but it's a matter of balance. How much reduction do we need to make for what would be regarded as normal production? So I've listed here a couple of specifications about the system. I mean, on a biological system, in this case, based under this certificate, The packing material runs at around 90 centimeters deep to get that level of contact. The pH for a biological scrubber tends to sit around 6.5 to 7.2. The backdrop on all scrubbers, we have to allow for a maximum of 65 pascals, but typically they would run a lot lower than that, probably around 20 to 25. In terms of reduction, I've listed what we would regard standard for this certificate, but then sort of demonstrating that you can upgrade by increasing the throughput or reducing the throughput of air across the packing material, allowing more contact time, which would mean further reductions in ammonia or odor. The point about that, of course, is that would require a bigger scrubber that comes at a slightly greater expense. On the right, I've done the same very much for chemical. The pH range for a chemical scrubber is between 3 to 4 pH, so on the acid side, but nothing stronger than Coca-Cola or an apple, so not terribly acidic, just enough to do the binding. And as you can see here, the higher level chemical scrubber runs at 90% ammonia reduction. The odor not as high as a biological process because that's better at reducing odor. So chemical tends to be delivering ammonia reduction. It produces as part of that process less wastewater than the biological, which is more focused on reducing odor reductions. I'm frequently asked in terms of wastewater, well, how much is produced and what do we do with it? And I've put a little chart here to say, well, typical 1,000 finisher pig production, biological air scrubber will produce more wastewater. It requires more fresh water, 915 cubic meters a year. It will produce around 515 cubic meters of wastewater. The byproduct is ammonium nitrate, running at around the pH of 7, and the nitrogen content of that is 2.8 kilograms. A chemical air scrubber, on the other hand, will need less water and produce less wastewater, 664 for the same amount, 646 for the same amount of animals, and producing 64 cubic meters of wastewater. The byproduct of this is ammonium sulfate, which runs at around the pH of 3 to 4. The nitrogen content is about 36.8. It's basically doing more binding, therefore producing more nitrogen from the process. And how we manage this will very much depend on what is permitted. You know, if we're going to spread it across the land as an organic fertilizer, then the management of it will be typically to treat the chemical wastewater with lime to neutralize the pH before spreading it. And if you can't do that, then it'll usually have to go off and be treated by a wastewater management company. So in conclusion, that's a very quick summary of what current air scrubbing is about. I was also asked to talk a little bit about the return on investment from air scrubbing. As you probably know, air scrubbing is seen as an unnecessary inconvenient cost by many, but over the last 10-15 years, we've been working very busy on how we can produce a return on investment from that. So this image that we're looking at the moment is an image of a pig house where we have an air scrubber at the end. So at the top of the roof, there's an exhaust chamber, and the air is going down into the pressure room, into the air scrubber. As part of this process, the warm air is heating the water in the air scrubber. And what we do is we use a plate exchanger to transfer the thermal energy from the wastewater into clean transportable energy, water, and transport it to a point in the house where we can use it to condition incoming air. So this is very interesting, for example, in a sow production where we have sow houses and piglet nurseries where the piglets need warming in the winter, and there's enough energy coming out of the sow houses to treat that. So looking at this in a little bit more detail, this is just a snapshot recently of a production in the Netherlands, where we experienced some very, very cold weeks in the winter. Where on the right you can see we have a source, which is the source of the energy, the wastewater. We're taking that from the scrubber at a temperature of 13.1 degrees. This is transported across the exchanger, and there's a slight drop down to 11.7, and then we take that to the inlet, and the incoming air at this point was minus 8.3. This incoming air is treated. We had a set point of 11.1. We managed to get the preconditioned air to 9.1 degrees. Okay, so that meant the air going into the house was treated to a level which then is supplemented in the first few weeks of the piglets cycle, but it creates a big financial benefit in terms of saving of energy. Down on the left side, you will see that at this particular point in the production, the COP, the transfer efficiency, that's the use of electrical energy to transfer thermal energy, was running at 22 COP, which meant we were using 1 kilowatt of electrical energy to transfer 22.6 kilowatts of thermal energy to a point in the house where we could condition air. Typically in production, because this was in a cold period, probably the system was working on overtime, but in typical cold winters, the average is around 40 to 50 COP. This is just a graph to show through a period of time. The green line is the temperature of the wash water during this period. The red line is what the inlet temperature is, fairly consistent, and then the blue line is the outside temperature. So you see some peaks and drops during the day, but the actual inlet temperature remained pretty consistent. Obviously, providing these energy systems, we are very busy with proving that they work. The benefit is twofold. It is recovering energy and obviously saving money, lowering the carbon footprint. But on the other side, because we commonly see, certainly in Northern Europe, during the cold periods, perhaps climate systems not being run as they should, and therefore creating other challenges for the animals. The thought behind this is that if we can precondition the air, that gives the farmer a lot more flexibility in how they ventilate the house, how they maintain good air condition, and the benefits that they receive from doing that in terms of how the animals perform. So by way of a little bit of proof that how this might work, this is a typical farm in the Netherlands. I think it's 400 sows. The cost of the system was, well, 116,000 euros. And then the savings in terms of energy saving a year was about 10,000, and an extra 10,000 because this farmer was using a heat pump for, I think it was for heating his delta tubes. And then savings in production in terms of feed improvement, lowering of mortality, etc., was around 16,000 a year. So the farmers, and these were numbers coming from the farmer himself, was probably saving around 30,000 in energy saving and production improvement, which when you get to match that with the cost of the system, it was a return of about 3.8 years. What we typically see with this system, the return on investment is normally around 4.5, 5 years for most production. In terms of what is the cost of an air scrubber, I was asked this by Ben Williams. We estimate the cost of a sow place in the Netherlands, full investment, is around 4,000 euros. And on this particular farm, using this air scrubber, the cost per sow place for the air scrubber was around 100 euros. So in the context of the complete investment, it's a fairly low cost overall for basically producing environmentally friendly animals. Finishers, probably around the 50 to 60 euros a finisher place. So in conclusion, Air scrubbing has advanced in the last 10 years. The systems are getting simpler. The focus is very much on that they are easy to maintain, because air scrubbing is about good maintenance, because if the system's not working optimally, it won't do the job. So that's the focus is to guarantee performance, and the simpler we make it, the easier to maintain it is, the better chance we have of doing that. Air scrubbing is a low cost compared to the overall spend on certainly on a new house. The system costs can be offset through energy recovery. I know I went through that quite quickly, but I hope that you can see that there are benefits that can be made from it. And of course, constantly in discussion in the future, environmental tariffs for the introduction of these sorts of systems will hopefully offset some of that cost. Something I didn't cover, and I've made a link at the bottom, if anyone gets the chance to click on this link, future systems will be integrated with preconditioning and dry cooling to further improve return on investment. This is something I haven't had time to cover today, but we also have an addition to this system where we introduce dry cooling, where we are reducing the humidity and maintaining temperatures of around 18 degrees throughout the year. So that all said and done, I hope that was interesting. It was fairly quick, and thank you for listening.